Tonight, as the room grows quiet, imagine now a single particle of light leaving the screen in front of you. It crosses the distance between the glass and your eyes so quickly that the journey feels instantaneous. One moment, the photon is part of an image on the screen. The next, it has entered your eye and become part of your experience of the world. Across a room, light seems infinitely fast, but it is not. Light has a speed, a precise speed. In the vacuum of space, it travels at 299 meters 792,458 meters every second, fast enough to circle Earth more than 7 times before a single second has passed. And yet, the universe is much larger than our imagination. If a beam of light left Earth and traveled toward the moon, it would not arrive immediately. It would spend a little more than 1 second crossing the darkness between the two worlds. A signal sent to an astronaut standing on the lunar surface would always carry that delay. If the same beam continued toward the sun, the journey would take about 8 minutes. The sunlight resting on your face today began its voyage while the world was still living 8 minutes in the past. And if the sun vanished at this moment, Earth would continue moving beneath its light for those same 8 minutes, unaware that farther out, the numbers begin to lose their familiarity. Light leaving the sun needs hours to reach the distant regions of the solar system. It needs more than 4 years to reach Proxima Centauri, the nearest star beyond our own. It would need roughly 100,000 years to cross the Milky Way from one side to the other. And to travel from the Andromeda galaxy to Earth, light must cross the darkness for about 2.5 million years. When you look toward Andromeda, you are not seeing it as it is tonight. You are seeing ancient light. Light that began its journey before modern humans existed, before cities, before writing, before anyone on Earth had ever looked upward and wondered what the stars might be. The fastest thing in nature carries the past with it. This is the first strange truth hidden inside the speed of light. The universe does not reveal itself all at once. It arrives slowly, piece by piece, carried across enormous distances by light that may have been traveling for years, centuries, or billions of years before reaching us. The night sky is not a picture of one moment. It is a mosaic of many different ages. The moon appears as it was just over a second ago. The sun appears as it was 8 minutes ago. Nearby stars appear as they were years ago. Distant galaxies appear as they were before Earth formed. Every direction is a different depth of time, and this raises a quiet but unsettling question. Why should reality have a speed limit at all? Why should information need time to travel from one place to another? Why can no signal cross the universe instantly? Why does nature permit this particular speed, but forbid anything with mass from reaching or passing it? We often speak of the speed of light as though it belongs to light alone, but it does not. It is woven into something much deeper. It is connected to the way space measures distance, to the way clocks measure time, and to the invisible boundary separating events that can influence one another from events that cannot. To understand it, we will need to leave behind the comfortable idea that space is one thing and time is another. Because the speed of light reveals that they are not separate. They are part of one structure. And somewhere inside that structure lies a stranger truth. The universe may not possess a single shared present at all. The idea that the universe may not share a single present sounds strange because, here on Earth, light usually hides its own delay. You turn on a lamp, and the room brightens at once. You look across the street, and every window appears to exist in the same moment. You raise your hand, and the mirror seems to answer immediately. At human distances, light is so fast that reality feels perfectly synchronized, but the illusion begins to fade the moment we travel beyond Earth. Imagine that we leave the planet behind and follow a single pulse of light outward through the solar system. The blue curve of Earth falls away beneath us. Within a little more than a second, the light reaches the moon. A message sent to an astronaut there must cross nearly 400,000 kilometers before it can arrive. If the astronaut answers immediately, the reply must make the same journey back. Even the simplest conversation contains a pause. Not because the equipment is slow, because the universe is large. The pulse moves on. In about 8 minutes, it reaches the sun. By then, Earth has already moved thousands of kilometers along its orbit. Nothing waits for light to catch up. Worlds continue turning beneath distant clouds. Light carries news of what happened, but never of what is happening now. Beyond the sun, the journey becomes quieter. Signals sent to Mars cannot control robotic explorers like remote cars. By the time a command arrives, the landscape may already have changed. At Jupiter, the delay grows longer. At Saturn, longer still. Near Neptune, sunlight that once crossed a room in less than a heartbeat has spent more than 4 hours moving through darkness. And still, the solar system has barely begun to reveal its scale. Far beyond the planets, the sun's influence gradually fades into interstellar space. A photon passes no sign, announcing that it has crossed the border. There is no wall, no gate, only one cosmic neighborhood slowly giving way to another. Then come the years. To reach Proxima Centauri, the nearest star beyond the sun, light must travel for more than 4 years. 4 years moving without rest. 4 years crossing a distance so great that ordinary units become almost useless. This is why astronomers speak in light years. A light year is not a measure of time. It is the distance light travels in 1 year, nearly 6 trillion miles. The Milky Way is roughly 100,000 light-years across. If a pulse of light began near one edge of our galaxy, when early humans were spreading across Earth, it might only now be arriving near the opposite side. The galaxy that appears as a silver mist in the night sky is a city of hundreds of billions of stars, separated by distances so vast that even light requires ages to move among them. And the Milky Way is only one galaxy. Andromeda lies about 2.5 million light-years away. The light reaching us from it tonight began its journey when our distant ancestors lived in a world without cities, writing, or recorded history. If someone in Andromeda could look toward Earth with an impossibly powerful telescope, they would not see our cities. They would not see our satellites. They would not see human civilization at all. They would see an ancient Earth. This changes what it means to look into space. We often imagine the universe as one enormous landscape surrounding us now, but no observer ever sees that landscape as one complete present. Every star is delayed. Every galaxy is delayed. Every image is a message that has spent time in transit. The farther away we look, the older the message becomes. A telescope does not simply magnify distant objects. It reaches backward through layers of cosmic history. Light from extremely distant galaxies began its journey when the cosmos was young, when galaxies were smaller, and when many of the elements that would one day become planets and people were still being forged. Distance becomes time, and time becomes distance. But another consequence is hidden inside this delay. The finite speed of light does not merely determine what we see late, it determines what we can see at all. There are regions whose light has not yet had enough time to reach us. Events may be unfolding beyond our present horizon, yet remain completely unknown to Earth. And there may be places so far away that the expansion of the universe will prevent their newest light from ever reaching us. In this sense, light draws an invisible boundary around every observer. Inside that boundary lies the portion of cosmic history that has had time to arrive. Outside, it lies a universe that may be real, vast and active, but still causally silent. Light is therefore more than a messenger. It is the edge of our knowledge. And yet, the strangest part is still ahead, because the speed we call the speed of light does not truly belong to light. Light simply reveals it. The phrase speed of light makes it sound as though this number belongs to light itself, as if photons carry a private rule through the universe, moving at one special velocity while everything else must remain behind. But modern physics suggests something deeper. The speed we call t is not merely a property of light, it is a property of space-time. Light travels at this speed because it is massless. Other massless disturbances, including gravitational waves, follow the same boundary. So light does not create the limit. It reveals it. Imagine that you are drifting through empty space in a silent spacecraft. Far ahead, another ship is moving away from you. You switch on a laser and send a pulse toward it. You measure the pulse traveling at 299,792,458 meters per second. Now imagine the other ship is already racing away at half the speed of light. Everyday intuition suggests that the crew aboard that ship should measure the laser moving past them more slowly. If you throw a ball from a moving train, someone on the ground and someone on the train do not measure the same speed. Velocities usually add and subtract, but light refuses to behave that way. The crew on the distant ship also measures the beam traveling at exactly the same speed. Not nearly the same, exactly the same. You could chase the beam faster and faster, but no matter how close your own ship came to the speed of light, the beam would still pull away from you at -2. This is not because light adjusts itself to match each observer. It is because space and time adjust instead. That is the strange bargain hidden inside relativity. If every observer must agree on the speed of light, then they cannot all agree on distance. They cannot all agree on how much time has passed. And they cannot all agree on which distant events happened at the same moment. The constancy of light is preserved because measurements of space and time change with motion. This is why t is better understood as a connection between space and time. In space-time, seconds and meters belong to one connected structure. The exact number, 299,792,458, can also be misleading if we treat it as a secret cosmic code. That number depends on the units human beings chose. Meters and seconds are our conventions. In fact, the modern meter is defined using the speed of light, so that light in a vacuum travels exactly 299,792,458 meters in 1 second. The deepest question is therefore not why nature chose that particular number. It is why the universe contains any finite invariant speed at all. Why should there be a boundary that every observer agrees upon? Why should space and time reorganize themselves to protect it? Atomic clocks, satellites, particle accelerators, and cosmic rays all behave as relativity predicts. But describing a rule does not necessarily explain why reality possesses it. The equations tell us what follows from it, and what follows is astonishing. Once the speed of light is the same for everyone, there can be no universal clock ticking identically across the cosmos. There can be no single measure of distance shared by all moving observers, and there can be no absolute answer to the question of what is happening right now in a distant place. This is where the speed of light stops being a fact about light and becomes a fact about reality. Imagine two observers floating between the stars. One is nearly motionless relative to Earth. The other crosses the same region at tremendous speed. Both look toward the same distant explosion. And yet they may disagree about how long a journey took, how far apart two events were, or whether another explosion happened before, after, or at the same time. Neither observer is mistaken. Neither has a broken clock. Neither occupies the privileged viewpoint of the universe. There is no privileged viewpoint. There are only different paths through space-time, each with its own measurements of distance and duration. The speed of light remains the same, Everything else becomes relative. That is why calling a speed limit is true, but incomplete. It is not like a law posted beside a road. It is built into the geometry of space-time itself. Objects with mass can move faster and faster, but the closer they approach the more energy is required. Their clocks separate further from the clocks they leave behind. Distances along their direction of travel contract. Light, having no rest mass, does not need to accelerate toward that boundary. It exists upon it. And when we follow that boundary carefully, we discover something more unsettling than any limit on speed. We discover that the universe does not contain one shared present. What you call now depends in part on how you are moving. And somewhere far beyond this quiet room, the present may not be a single moment waiting to be found. It may be a question with more than one correct answer. Most of us move through life with the quiet assumption that the universe shares one common present. Somewhere, we imagine, there is a single, invisible moment stretching across everything. A moment that includes this room, the far side of Earth, the surface of Mars, the center of the Milky Way, and every distant galaxy beyond it. We call that moment now. It feels obvious, but the speed of light reveals that this shared cosmic present does not exist. To see why, imagine a long train moving smoothly through the night. Inside the train sits a passenger at the exact center of the car. Outside, on the platform, stands another observer. At one instant, two flashes of lightning strike the railway. One strikes far ahead of the train. The other strikes far behind it. The observer on the platform is positioned exactly halfway between the two flashes. Light from both strikes reaches them at the same time. From that observer's perspective, the lightning strikes were simultaneous. They happened together. Now consider the passenger inside the moving train. The passenger is also positioned at the center of the train car, but while the light is traveling, the train is moving forward. The passenger moves toward the light coming from the front strike and away from the light coming from the rear strike. As a result, the light from the front reaches the passenger first. The light from the rear arrives later. The passenger concludes that the front lightning strike happened before the rear one. At first, this may seem like a simple difference in when the light arrived. Perhaps, you might think, both strikes still happened at the same time, and the passenger merely received the information unevenly. But that explanation fails once we remember the central rule. Both observers measure light moving at the same speed. Neither observer can say that one beam traveled faster than the other, and neither observer occupies a more correct or more fundamental position in the universe. For the person on the platform, the strikes were simultaneous. For the person on the train, they were not. Both conclusions are correct within their own frame of motion. This is the relativity of simultaneity. It is one of the deepest consequences hidden inside the speed of light. Events that are simultaneous for one observer may occur at different times for another observer moving relative to the first. The disagreement is not caused by faulty clocks. It is not caused by slow communication. It is not an illusion created by perception. It is built into space-time itself. The universe does not provide a single answer to the question, what is happening right now at a distant place? The answer depends partly on how the observer is moving. Here on Earth, this effect is tiny. Our everyday speeds are far too slow compared with light for the difference to become noticeable. Cars, trains, airplanes, and even spacecraft move through a world where the relativity of simultaneity is hidden beneath ordinary experience. But across enormous distances, or at speeds close to light, the difference becomes real and unavoidable. Imagine two events taking place in distant galaxies. Perhaps one star collapses in a galaxy millions of light years to the left. At nearly the same time, another star is born in a galaxy millions of light-years to the right. An observer moving one way may calculate that the collapse happened first. Another observer moving in the opposite direction may calculate that the birth happened first. A third observer may calculate that both events happened at the same time. There is no universal clock suspended above the cosmos to decide which observer is correct. There is no hidden master timeline that all motion must follow. There are only observers, events, and the geometry connecting them. This does not mean that time is imaginary. It does not mean that reality is subjective. And it does not mean that any sequence of events can be rearranged at will. Events connected by cause and effect preserve their order. If one event sends a beam of light that causes another event, every observer will agree about which came first. Cause remains before effect. But events too far apart to influence one another can have no universal ordering. Their relationship in time depends on the observer's motion. This divides the universe in a way that is almost impossible to picture from ordinary life. Close events seem to share a common present. Distant events do not. The farther apart they are, the more uncertain the idea of a shared now becomes. Consider the Andromeda Galaxy. It lies about 2.5 million light-years away. We can ask what is happening there right now. Perhaps a star is exploding. Perhaps a planet is forming. Perhaps nothing unusual is happening at all. But relativity tells us that right now in Andromeda is not an absolute slice of reality. Two observers passing Earth at different speeds can assign different distant events in Andromeda to the same moment on Earth. One observer's present in Andromeda may lie slightly ahead of another observer's. The difference may be small at ordinary speeds, but over millions of light-years, even a small change in motion can shift the assigned present by a significant amount. The idea is strange because consciousness makes the present feel universal. Your thoughts occur now. The room exists now. The sound of a voice reaches you now. The stars above appear to belong to this same moment. But the stars are not part of one shared instant. They are messages from different times. And even beyond what we can see, the concept of one universal present dissolves. Somewhere, a world may be circling a distant star. Its oceans may be moving beneath an unfamiliar moon. Its clouds may be rising and falling. Yet there is no single cosmic command that places one precise moment on that world beside this precise moment in your room. Space-time does not organize itself into one universal stack of present moments. Different observers divided into space and time in different ways. What one observer calls distance, another partly interprets as time. What one observer calls simultaneous, another separates into earlier and later. And through every disagreement, the speed of light remains unchanged. It is the fixed point around which our measurements bend. This may be the strangest truth we have encountered so far. The universe is not moving forward beneath one enormous clock. There is no heartbeat shared by all galaxies. There is no single moment passing everywhere at once. There are countless paths through space-time, countless clocks, countless definitions of distant now. And yet, every observer still finds the laws of physics working perfectly. The universe does not need a common present in order to remain consistent. It needs something else. It needs a structure that tells each observer how space, time, and light fit together. And once that structure is understood, another consequence quietly appears. If observers do not agree on which distant events happen at the same time, then they will not always agree on how much time passes between events either. Motion does not merely change the present. Motion changes time itself. If motion changes what different observers call the present, then it must also change the way they measure the passage of time. This is not a philosophical suggestion. It is a physical effect. Clocks moving at different speeds do not always remain synchronized. A traveler moving quickly through space can experience less time than someone who stays behind. To understand why, imagine the simplest clock possible. Picture two perfectly aligned mirrors facing one another inside a spacecraft. Between them, a pulse of light moves upward and downward, reflecting from one mirror to the other. Each complete journey marks one tick: up, down, up, down. To an observer resting inside the spacecraft, the pulse follows a straight vertical path. The distance between the mirrors is fixed, and the light crosses that distance at the speed of light. The clock seems ordinary. Now imagine watching the same spacecraft pass from the outside. As the ship moves forward, the mirrors move with it. The pulse of light can no longer appear to travel only upward and downward. While the light is crossing the gap, the upper mirror has shifted forward. To reach it, the pulse must travel along a diagonal path. Then, as it returns, the lower mirror has moved forward as well, creating another diagonal. From outside the spacecraft, the light follows a longer path, but both observers must still measure the same speed of light. The pulse cannot travel faster for the outside observer simply because its path is longer. So if the distance is greater and the speed remains unchanged, something else must increase: the time between ticks. The moving clock runs more slowly. This is time dilation. It does not mean the clock is damaged. It does not mean its machinery is resisting motion. Every process inside the spacecraft slows by the same amount from the perspective of the outside observer. The beating of a heart, the movement of atoms, the chemistry of a thought, the aging of a body. Inside the ship, everything feels completely normal. The traveler does not feel time dragging. Their clock ticks once per second. Their breathing remains steady. Their thoughts arrive at the usual rhythm. It is only when their clock is compared with another clock following a different path through space-time that the difference appears. At the modest speeds of ordinary life, the effect is almost invisible. A car traveling down a highway experiences a tiny amount of time dilation. An airplane experiences more. A spacecraft experiences more still. But all of these differences are far too small for the human body to notice. Precision instruments can notice them. Atomic clocks placed on fast-moving aircraft have returned showing slightly different times from clocks left on the ground. Particles created high in Earth's atmosphere provide another example. Muons are unstable particles with extremely short lifetimes. At rest, many of them should decay long before reaching the surface. Yet when they travel toward Earth at speeds close to light, large numbers survive long enough to be detected at ground level. From our perspective, their internal clocks are running slowly. From the muons' perspective, the atmosphere is compressed along their direction of motion, allowing them to cross the distance before they decay. Both descriptions are valid. Time changes. Distance changes. The speed of light does not. This same effect quietly operates in the technology surrounding modern life. Satellites carry precise clocks as they move rapidly above Earth. Their motion causes their clocks to run at a slightly different rate from clocks on the ground. Gravity also changes the passage of time, adding another correction from general relativity. Without accounting for these effects, navigation systems would gradually lose accuracy. A theory that seems distant and abstract becomes part of an ordinary journey through a city. But the full meaning of time dilation becomes clearer in a more personal story. Imagine two twins standing together before a spacecraft. They are the same age. Their clocks are synchronized. One remains on Earth. The other boards the ship and begins a long journey toward a distant star. The spacecraft accelerates until it is moving at a substantial fraction of the speed of light. It travels through the darkness, turns around, and eventually returns home. For the twin aboard the ship, perhaps only a few years have passed. The journey felt long, but not impossible. Meals were eaten. Sleep came and went. The ship's clocks behaved normally. But when the traveler steps back onto Earth, the twin who stayed behind is older. Perhaps much older. More time has passed along the path through space-time taken by the twin on Earth than along the path taken by the traveler. This is often called the twin paradox, though there is no true contradiction. The two twins do not follow equivalent journeys. The traveling twin changes direction, accelerates, and returns. The twin on Earth remains within approximately the same frame throughout the trip. Their paths through space-time are different. And different paths can contain different amounts of elapsed time. This is one of the most unsettling aspects of relativity. Time is not simply a river flowing at one universal rate. It is more like a distance measured along a path. Two travelers can leave the same event, follow different routes through space-time, and reunite having experienced different amounts of life. The faster one moves through space, the less time may pass along that journey compared with someone who remains behind. As the traveler approaches the speed of light, the effect becomes increasingly dramatic. A voyage that spans decades or centuries from Earth's perspective may feel far shorter aboard the ship. This raises the possibility of traveling into the future, not by disappearing and reappearing through a machine, but by moving so quickly that less time passes for you than for the world you leave behind. You could depart from Earth, travel near the speed of light, and return to find that generations had passed. The planet would still be familiar, and yet almost everything on it could have changed. Cities, languages, borders, perhaps even the species that once waved goodbye. Relativity allows this kind of journey into the future, but it does not offer an equally simple path back into the past. The speed of light seems to protect the order of cause and effect. It permits different clocks to disagree. It permits different observers to disagree about distant simultaneity, but it does not permit a massive object to accelerate through the boundary and emerge beyond it. The closer the spacecraft comes to light speed, the more energy is required to increase its velocity further. The gains become smaller. The cost becomes greater. To reach the speed of light would require an unlimited amount of energy for any object with mass, so the boundary remains unreachable. Light itself travels along that boundary. But here, language must be used carefully. It is tempting to say that time stops from the photon's perspective, or that a photon experiences its entire journey instantly. Yet relativity does not allow us to define a valid resting frame for light. There is no perspective in which a photon is motionless and the rest of the universe moves around it. What physics can say is that the proper time along a path traveled by light is zero. The mathematical interval between emission and arrival differs from the interval experienced by a massive traveler. But we cannot meaningfully ask what the photon sees, remembers, or feels. Light does not provide us with a traveler's diary. It provides us with a boundary, and the closer matter moves toward that boundary, the more dramatically time and distance must change to preserve it. Which brings us to the next stage of our journey. If you could board a spacecraft and move close enough to the speed of light, the universe outside your window would no longer resemble the quiet night sky you know. Colors would shift. Starlight would gather ahead. Distances would contract. And the path to the stars would become shorter for you, even as centuries continued to pass far behind. Imagine now that the spacecraft is ready. The cabin is quiet. The lights are dim. Beyond the window, Earth hangs beneath you like a blue lantern suspended in darkness. At first, nothing about the journey feels unusual. The engines awaken gently. The planet begins to shrink. Clouds become pale swirls. Oceans merge into a single curve of blue. The lights of cities disappear into the night side of the world, and the moon drifts slowly across the black. You are moving faster with every passing minute. But the stars still look familiar. Orion remains where you remember it. The Milky Way still forms a faint river across the sky. The constellations seem permanent, as though they have been waiting in the same arrangement since the beginning of time. Then, the spacecraft continues to accelerate. 10% of the speed of light. 20%. Half the speed of light. The universe outside the window begins to change. Not because the stars themselves are suddenly different, because your motion is changing the light that reaches you. Ahead of the spacecraft, you are moving toward incoming waves of light. Their wavelengths become compressed. Red light shifts toward orange. Orange shifts toward yellow. Visible light moves toward blue. Light that once existed beyond the visible spectrum may be shifted into colors your eyes can detect. Behind the spacecraft, the opposite occurs. The waves are stretched. Blue light moves toward red. Red light slips into the infrared and disappears from sight. The sky behind you slowly darkens. Ahead, the universe grows brighter. More and more light is concentrated into the direction of travel. Stars that once seemed scattered across the sky begin to gather toward a smaller region in front of the ship. The effect is not unlike wind-driven rain striking the windshield of a fast-moving car. The faster you move, the more of the universe appears to rush toward you from ahead. But this is not rain. It is starlight, radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays. Energy from across the spectrum is being shifted, compressed, and focused by your motion. A gentle glow in ordinary space can become dangerous at relativistic speed. Photons that were once harmless may strike the spacecraft with far greater energy. Tiny grains of interstellar dust, nearly insignificant at low speed, can become destructive projectiles. The path between the stars is not truly empty. It contains thin gas, dust, radiation, and particles moving through the dark. At near light speed, even emptiness becomes something the ship must survive. Outside the window, the familiar geometry of the sky begins to bend. Stars that once appeared beside you seem to move forward. Your field of view changes. Light arriving from wide angles is drawn toward the direction of travel, creating the impression that more of the universe has been compressed into the space ahead. It may seem as though you are looking down a brilliant tunnel made of stars. Behind you, the sky becomes dimmer and redder. Ahead, it becomes narrower, brighter, and increasingly blue. You have not entered another universe. You are seeing the same one from a radically different path through space-time. Now imagine that the spacecraft reaches 99% of the speed of light. Earth is far behind. The engines grow quiet. Inside the cabin, your body feels normal. Your heartbeat has not slowed. Your thoughts have not become heavy. A second still feels like a second. You can walk across the room, pour a drink, close your eyes, and sleep. Nothing inside the spacecraft announces that time is behaving differently, but the distance ahead is no longer measured in the same way that people on Earth measure it. To observers who remained behind, the nearest stars are still separated by several light years. For you, moving near the speed of light, the distance in the direction of travel is contracted. The destination has not physically moved closer in some universal sense. Rather, space and time are divided differently along your path. A star that lies many light years away in Earth's frame may be reached in a much shorter period of your own time. This is how relativity makes interstellar travel less impossible for the traveler, though never easy. Suppose your ship moves toward a star 100 light-years from Earth. To people watching from home, the journey must take a little more than 100 years because the ship cannot move faster than light. But aboard the spacecraft, if you travel close enough to the limit, far less time may pass. Perhaps decades. Perhaps years. At even greater speeds, the traveler's time could become shorter still. You could cross distances that seem larger than a human lifetime and remain alive to reach the other side. But the universe does not offer this gift without a cost. The shorter the journey becomes for you, the more time passes for those you leave behind. Messages from Earth arrive increasingly altered and delayed. Voices from home become records of another era. People age. Children grow old. Cities change. The world continues beneath a sky you no longer share. Imagine reaching the distant star, turning the spacecraft around, and beginning the journey home. From your perspective, the voyage may have lasted only a portion of your life. You remember Earth almost as it was. The streets, the language, the faces waiting at the launch site. But when the planet finally appears again as a pale blue point, you are returning not merely from a distant place. You are returning to a distant time. A century may have passed, or 1,000 years. The continents remain, but coastlines may have changed. The names of nations may have vanished. The people you knew exist only in archives, if their names survive at all. The voyage allowed you to cross the stars. It did not allow you to preserve the present. Near-light travel is therefore not only a journey through space. It is a one-way passage into the future. The faster you move, the more completely you separate yourself from the time of the world behind you. There is something both beautiful and lonely in this possibility. A traveler may reach stars no human being has ever touched. They may see planets beneath alien suns. They may cross distances once thought impossible. But each victory over distance deepens the distance in time. The ship arrives. The traveler survives. And home becomes ancient. Still, even such a spacecraft never reaches the speed of light. As its velocity rises, each additional increase requires more energy than the one before. The ship can approach the boundary. It can travel so close that the difference appears almost invisible, but it cannot cross. For matter, the edge remains forever ahead, and perhaps that is not merely a technological limitation. Perhaps it is a protection built into reality itself. Because beyond the question of how fast something can move lies a more important question. What events can influence one another? What can cause what? And which parts of the universe are separated not only by distance, but by the very structure of causality? To answer that, we must leave the spacecraft behind and look at the invisible shape created whenever a pulse of light begins to travel. A shape that surrounds every event, every star, every world, and every moment of your life. Imagine a single event in the darkness. A star flares. A transmitter sends a signal. A person turns on a lamp in a quiet room. From that instant, light begins to move outward. Not in one direction, but in every direction at once. In open space, the light forms an expanding sphere. 1 second later, that sphere has a radius of nearly 300,000 kilometers. 1 year later, it has expanded to a radius of 1 light-year. Anything inside it can, in principle, know that the event happened. Anything outside it cannot. Not yet. This expanding shell of light gives us one of the most useful pictures in modern physics. A light cone. Picture space, spread flat like a dark sheet, with time rising upward. At the center is the event itself. As light moves outward through space and forward through time, the expanding sphere becomes the widening surface of a cone. The future opens above it. the past narrows below. And every event in the universe has a cone like this. Every heartbeat, every explosion, every collision between particles, each one sends influence outward, limited by the speed of light. The lower half is called the past light cone. It contains everything that could have influenced the event at its center. The sunlight that reached Earth, the gravity of the moon, the signals that entered a telescope, the ancient starlight that crossed the galaxy before touching your eye. The upper half is the future light cone. It contains every event that the present moment may one day influence. A radio message sent tonight may enter that future. A beam of light leaving Earth may cross the orbit of Mars, then Jupiter, then the darkness beyond the solar system. Far in the future, it may pass a distant star. Within the future light cone, cause can become effect. A signal can arrive. A particle can collide. A decision can change what happens next. But outside the cone lies another region, a region sometimes called elsewhere. Events there are too distant and too close in time for any signal traveling at or below the speed of light to connect them with you. They cannot have caused this moment, and this moment cannot yet affect them. They are not unreal. They are simply separated from you by the structure of space-time. Imagine that two distant stars explode on opposite sides of the galaxy. Their light has not reached Earth. Earth has not influenced those explosions. For now, the events exist outside one another's light cones. No message can pass between them quickly enough to establish a cause and effect relationship. This is why the speed of light is more than a limit on motion. It is a limit on influence. It decides which parts of reality may be connected by causality. And this may explain why nature guards the boundary so carefully. Suppose information could travel faster than light. At first, that sounds useful. Messages could cross the solar system instantly. Civilizations could communicate across the galaxy without waiting centuries. But relativity makes the situation far stranger. Because observers in different states of motion divide space and time differently, a faster-than-light signal in one frame can appear to travel backward in time in another. The order of events may reverse. An answer could appear before the question was sent. A warning could arrive before the danger that caused it. With the right arrangement of motion and signals, a message might return to its sender before it was transmitted. Cause and effect could fold into a loop. The universe could become capable of contradicting its own history. This does not prove that every imagined faster-than-light idea is impossible in every future theory. But within relativity, the light-speed boundary protects a consistent order of causation. It prevents ordinary signals from escaping their light cones. It keeps effects from arriving before their causes. The limit that seems to imprison us may also be what keeps reality coherent. The universe does not need one universal present, but it does need a reliable structure telling events how they may influence one another. The light cone provides that structure. And once you begin to see the universe this way, distance takes on a new meaning. A distant galaxy is not merely far away. It may lie outside the region you can affect today. A star may be visible because its ancient light entered your past light cone, while your newest light may never reach the star as it exists now. Two regions can be visible to one another through old messages, yet already be moving toward permanent causal separation. Even here on Earth, your life unfolds inside these invisible boundaries. The light entering your eyes comes from your past cone. The words you speak move into your future cone. The warmth leaving your body, the sound of your breathing, and every signal around you travel outward into events that have not happened yet. Moment by moment, you stand at the meeting point between a cone of causes and a cone of possible consequences. Behind you lies everything that could have shaped this instant. Ahead lies everything this instant may still touch. Beyond both lies a vast elsewhere, real but unreachable for now. And in the quiet geometry between them, the speed of light holds the boundary. But this same boundary also places every observer inside a private horizon of visible history. All the light you receive has traveled from somewhere in your past. Every star in the sky belongs to a different layer of that past. And every telescope can only collect messages that have had enough time to arrive. To look deeper into space is therefore to look deeper into the light cone behind us. It is to watch the universe become younger with distance. And that means the night sky is not merely filled with stars. It is filled with time. Step outside on a clear night and look toward the moon. The light entering your eyes has already completed a journey. It left the lunar surface a little more than 1 second ago, crossed the space between two worlds, passed through Earth's atmosphere, and finally reached you. The moon you see is not the moon of this exact instant. It is the moon of the recent past. The delay is small enough to feel unimportant. But when we turn toward the sun, the gap grows. Sunlight needs about 8 minutes to reach Earth. The warm light resting on a window, the glow on the horizon, and the shadows beneath the trees all began at the sun several minutes earlier. We never see our star as it is now. We see it as it was. And as our gaze moves farther into the night, the past becomes deeper. Sirius, the brightest star in Earth's night sky, appears to us through light that has traveled for more than 8 years. Vega appears through light that began its journey roughly 25 years ago. Betelgeuse appears through light that may have crossed space for hundreds of years before entering our telescopes. If Betelgeuse were to explode tonight, Earth would not know until the final light reached us. The event would already be over. The star would already have changed. Yet our sky could continue showing the older version for centuries. This is not an illusion created by telescopes. It is the only way the universe can be observed. Every act of seeing depends on light traveling from an object to an observer. Even the face of someone standing across the room belongs to a tiny fraction of a second in the past. The delay is far too small to notice, but it is never truly zero. We do not see the present directly. We receive light from what has already happened. On cosmic scales, this simple delay transforms astronomy into a form of time travel. A telescope does not travel physically into the past. It remains here, beneath the same sky as the observer. But by collecting older and older light, it allows us to witness earlier and earlier chapters of cosmic history. When a telescope studies the Andromeda galaxy, it sees a galaxy from about 2.5 million years ago. When it studies galaxies billions of light years away, it sees them when the universe was far younger than it is today. Some appear small, irregular, and crowded with young stars. Others are caught in the process of merging. Their ancient light reveals a time when the calm spiral galaxies of the modern universe had not yet fully formed. This means the night sky is not one picture. It is many eras layered together. Nearby objects belong to the recent past. Distant stars belong to older centuries. Remote galaxies belong to times before Earth existed. And the faintest light we can study carries us toward the childhood of the universe itself. Long before stars and galaxies formed, the cosmos was filled with hot, dense matter and radiation. For hundreds of thousands of years, the universe was too hot for light to travel freely across great distances. Photons scattered constantly from charged particles, trapped in a glowing cosmic fog. Then the universe expanded and cooled. Electrons joined with atomic nuclei. Space became transparent. The light released from that ancient transition began traveling outward, and much of it is still traveling today. We detect it as the cosmic microwave background. It arrives from every direction. A faint afterglow from a time when the universe was only about 380,000 years old. The light has stretched as the universe expanded, shifting from a hot glow into microwaves far beyond human vision. Yet hidden inside that faint radiation are tiny variations, slight differences in temperature, small unevenness that would later grow into galaxies, clusters, stars, planets, and eventually observers capable of looking back. When we study this light, we are not looking at an object in the usual sense. We are looking at an ancient surface surrounding us in every direction, the oldest light that can travel freely through the universe. Beyond it, earlier times are hidden from ordinary light. There were moments before the cosmic microwave background, but photons cannot bring us a clear image from that era. The universe itself was opaque, so even light, the great messenger, has limits on what it can reveal. Every telescope is therefore both a window and a boundary. It shows us worlds that would otherwise remain invisible, but it can only show what has sent light toward us and what has existed long enough for that light to arrive. There may be planets forming tonight whose first light will not reach Earth for thousands of years. There may be stars that have already vanished, though their old glow still rests in our sky. There may be distant civilizations whose entire histories have unfolded, while their earliest signals are still crossing the dark. And if someone far away is looking toward Earth, they do not see us as we are now. At a distance of 100 light-years, they see Earth from 100 years ago. At a distance of 1,000 light-years, they see a world before modern technology. From 2.5 million light-years away, Earth would appear long before human civilization. The universe does not exchange complete, immediate knowledge of itself. It sends old messages, quiet fragments of history crossing the dark. This gives the sky a strange and beautiful stillness. The stars appear present, yet each belongs to another time. Some shine from years ago, some from millennia ago. Some galaxies shine from an age before the sun was born. You can stand beneath one sky and receive light from countless chapters of existence. There is no single age above you. There is only a layered archive. And still, there are places where even these ancient messages cannot escape. Regions where the paths of light bend inward so completely that no future observer outside can receive them. To find those places, we must follow the light toward one of the darkest boundaries in the universe, the horizon of a black hole. A black hole is often described as an object with gravity so strong that even light cannot escape. That description is true, but it can also be misleading. It may sound as though light tries to climb away, gradually slows, and finally loses its struggle against gravity. That is not quite what happens. Locally, light always moves at the same speed. Even near a black hole, a nearby observer would still measure a passing photon traveling at the speed of light. The photon does not become tired. It does not run out of momentum. It does not slow to a stop. What changes is the structure through which it moves. Space-time itself bends. Imagine approaching a black hole from far away. At first, the stars behind it appear distorted. Their light follows curved paths through the warped space surrounding the object. A single background star may appear in more than one place. Light can wrap around the darkness, forming glowing arcs, or even a nearly complete ring. The black hole does not emit light of its own, yet the geometry around it reshapes the light of everything behind it. As you move closer, the curvature becomes more extreme. The invisible light cones, surrounding every event, begin to tilt. Far from the black hole, part of a light cone points outward, and part points inward. A photon may choose a path toward the black hole, or a path away from it. There are still roads leading home, but closer to the horizon, those outward roads become narrower. More possible paths lean toward the black hole. The future itself appears to tilt inward. Then comes the event horizon. It is not a solid surface. There is no wall waiting in the dark. There may be no sudden flash, no collision, and no sign suspended in space announcing that the boundary has been crossed. The horizon is a boundary in causality. Outside it, a signal can still travel outward and influence the wider universe. Inside it, every future-directed path leads deeper in. Even a beam of light aimed away from the center cannot escape. This is not because it is moving too slowly. It is because, inside the horizon, moving toward the center is as unavoidable as moving toward tomorrow. The center is no longer merely a place located ahead in space. It lies within the future of everything that has crossed the boundary. To turn away from it would be like turning away from the next moment of your life. The geometry offers no such direction. For a distant observer, the story appears different. Imagine watching a small probe fall toward the black hole. As it approaches the horizon, the light it sends outward must climb through increasingly curved space-time. Each signal reaches you with less energy than the one before. The light becomes redder. The intervals between signals become longer. The probe appears to slow. Its image grows dim. Eventually, it fades beyond detection. From far away, you never clearly watch it cross the horizon. Its final visible light is stretched and weakened until it disappears into the darkness. But aboard the falling probe, time does not suddenly freeze. Its clocks continue ticking. The horizon may pass without any dramatic local event, especially if the black hole is enormous and tidal forces there are still gentle. The probe crosses the boundary in a finite amount of its own time. Outside and inside descriptions seem different because observers divide space-time differently. The distant observer organizes events using clocks far from the black hole. The falling observer follows a path directly through the curved region. Both descriptions belong to the same geometry. Neither requires light to stop moving. This is one of the most important lessons black holes teach us. The speed of light alone does not determine whether escape is possible. The shape of space-time determines where light can go. A photon always follows a path available to it. Near a black hole, those paths bend. At the horizon, the last outward path runs along the boundary itself. Inside, all paths point inward. The speed remains unchanged. The meaning of outward disappears. There is something quietly unsettling about this. We often imagine direction as permanent. Up remains up. Away remains away. The future remains open. But near a black hole, geometry rearranges those ideas. A destination can become part of the future. A boundary can exist without matter. A region can remain visible from the outside, while no message from its interior can ever return. The event horizon separates two parts of reality, not by distance alone, not by a physical barrier, but by the impossibility of future communication. Everything crossing it may continue to exist for a time. It may move, fall, and encounter whatever waits deeper inside. But its story is removed from the future light cones of the external universe. No signal can bring that story back. In this way, a black hole creates a private region of space-time, a place still connected to the universe that formed it, yet unable to send any new influence outward. The horizon is therefore not simply where gravity becomes strong. It is where causality closes in one direction. And black holes are not the only places where horizons appear. There is another boundary surrounding us now. It is not formed by a collapsed star. It is not located at one dark point in the sky. It emerges from the expansion of the universe itself. Beyond that boundary may lie galaxies whose ancient light we can still receive, but whose future we can never touch. Galaxies moving toward a silence deeper than any black hole, not because their light has stopped, but because the space between us is growing faster than new messages can cross it. The expansion of the universe is easy to imagine incorrectly. It is tempting to picture galaxies racing outward through a vast, empty arena, like fragments from an explosion. But the deeper reality is stranger. On the largest scales, galaxies are not simply moving through space. The space between them is expanding. Imagine a field of distant islands resting on the surface of a dark, stretching ocean. The islands may remain nearly still within their local waters, yet the ocean itself grows wider between them. No single island needs to sail away. The distance increases because the surface beneath them is changing. Something similar happens across the cosmos. Within galaxies, gravity holds stars together. Within groups and clusters, gravity can keep neighboring galaxies bound. The Milky Way and Andromeda, for example, are moving toward one another, not apart, but across the enormous spaces between distant galaxy groups. Cosmic expansion becomes dominant. The gaps grow, and as the universe ages, those gaps can grow faster and faster. This does not mean that galaxies are locally breaking the speed limit of light. A nearby observer beside any one of them would still measure light moving normally at the same familiar speed. No spaceship passes another local observer faster than light. No photon violates the laws of relativity. The effect comes from the changing geometry of the universe itself. The distance between very remote regions can increase at an effective rate greater than the speed of light because more and more expanding space lies between them. That kind of separation is not the same as an object flying past you through space. And this distinction creates one of the most haunting truths in cosmology. Some galaxies are visible to us today, yet may already be beyond our future reach. The light entering our telescopes from those galaxies began its journey long ago, when they were closer to us, and when the universe had expanded less. That ancient light continued traveling, while space stretched beneath it. After billions of years, it finally arrived. We can see the galaxy as it once was. We can study its stars. We can measure its motion. We can place its image on a map. Yet a signal transmitted from Earth tonight may never reach the same galaxy. The path ahead has changed. The space between us may now be expanding so rapidly that the signal can travel forever at the speed of light and still fail to close the growing distance. The galaxy remains visible through its past, but it is unreachable in its future. This is the difference between the observable universe and the reachable universe. The observable universe includes everything whose light has had enough time to arrive since the early cosmos became transparent. It is an enormous sphere of visible history surrounding us. But visibility does not guarantee contact. Some places we see belong to regions we can no longer influence. Their ancient photons have entered our past light cone. Our newest photons may never enter their future. In a quiet sense, we are receiving farewell messages from worlds that have already crossed beyond communication. No alarm marked the moment. No wall appeared between us. The galaxies did not suddenly vanish. Their older light continued arriving, century after century, carrying images from a time when connection was still possible. But the universe expanded, the distance widened, and eventually, a horizon formed. This horizon is not the same as the event horizon of a black hole, though the two share a family resemblance. Both are boundaries defined by what signals can do. Near a black hole, Space-time bends so severely that light cannot escape outward. Across the expanding universe, space grows in such a way that light from beyond a certain region can never reach us if emitted too late. In both cases, the boundary is about causality. What can still influence what? What can still send a message? What has become permanently silent? Imagine a civilization living in one of those remote galaxies. Perhaps they look into their own sky and study ancient light from the Milky Way. Perhaps they see our galaxy as it existed before the sun formed. Perhaps their instruments detect the faint structure of a spiral that has not yet produced Earth. They might ask whether life will ever appear here. But by the time humanity exists, the separation may already be too great. Our first radio signals leave Earth. They pass the Moon. They cross the outer solar system. They enter interstellar darkness. Yet however long they travel, the expansion ahead may prevent them from ever reaching that distant civilization. Two worlds can exist in the same universe and still be denied any possible future conversation, not because either is hidden, not because the signal is weak, but because the geometry between them has placed each beyond the other's causal horizon. In the far future, this separation will become more complete. If cosmic expansion continues accelerating, distant galaxies outside our local gravitational neighborhood will appear increasingly red. Their light will be stretched to longer wavelengths. Their clocks will seem to slow. Their images will fade. Over immense spans of time, many will disappear beyond detectability. Future observers in the Milky Way may look outward and see a much emptier cosmos. The great web of galaxies visible to us today could be gone from their sky. Only the galaxies gravitationally bound to our local group may remain visible. The evidence of a vast expanding universe may become far harder to discover. Those future astronomers might live inside a dark island of stars, surrounded by what appears to be endless emptiness. The universe would still extend beyond them, but its distant light would no longer arrive. This gives our own era a rare position in cosmic history. We live at a time when the universe is old enough for galaxies, planets, and observers to exist, yet young enough for light from vast regions to remain visible. We can still see the large-scale structure of the cosmos. We can still detect the ancient afterglow of the beginning. We can still watch remote galaxies before expansion carries their future beyond us. The night sky is therefore not only an archive, it is a temporary archive. Some pages are still arriving. Others have already stopped being written for us. The speed of light gives the universe time to reveal itself. Expansion decides how much of that revelation can ever reach us. And somewhere beyond the dimming edge are galaxies whose stories continue without any possibility of entering ours. They may form new stars. Their stars may build planets. Their planets may produce oceans, weather, chemistry, and perhaps life. But no future telescope on Earth will see those later chapters. No message from us will announce that we were here. The separation will not be measured only in miles or light years. It will be absolute. A boundary between possible connection and permanent silence. We began this journey by asking why light has a finite speed. Now we can see that the question reaches far beyond motion. That speed shapes what can be known, what can be changed, what can remain connected, and what must slowly disappear beyond the horizon. Still, one mystery remains. Why should the universe be built around this boundary at all? Why should space and time rearrange themselves to preserve it? Why should causality, horizons, and the visible cosmos all depend upon one invariant speed? We know what the speed of light does, but do we know why it exists? We have followed light across a room, beyond the moon, past the stars, into black holes, and toward galaxies that are slowly disappearing beyond our future reach. At every stage, the same boundary remained. The speed of light connected distance with time. It shaped the order of cause and effect. It determined what could be seen, what could be reached, and what could never communicate with us again. And now we arrive at the question that has been waiting quietly beneath the entire journey. Why? Why should the universe possess a finite speed that no material object can reach? Why should every observer measure the same value, even while moving differently? Why should space and time bend their measurements around this one invariant limit? Physics can describe the consequences with extraordinary precision. The equations of relativity tell us how clocks change with motion, how distances contract, how light cones divide possible causes from possible effects, and how gravity reshapes the paths available through space-time. Experiments agree. Atomic clocks disagree by exactly the amounts predicted. Fast-moving particles survive longer than they otherwise should. Satellites require relativistic corrections. Gravitational waves cross the universe at the same fundamental speed as light. Again and again, nature behaves as though this limit is not an accident. It is structural. But knowing how a rule operates is not always the same as knowing why the rule exists. The number 299,792,458 meters per second may seem mysterious, but the number itself is partly a product of human units. We chose the meter. We chose the second. In another system, the same speed could be represented by a different number. Physicists often simplify their equations by choosing units in which the speed of light is simply 1. In that language, the limit no longer looks like an enormous number. It becomes a conversion between space and time. 1 unit of time corresponds to 1 unit of distance along the path of light. This suggests that the speed of light may be less like the speed of an object and more like the exchange rate between two aspects of space-time. It tells us how much time is woven into distance, how much distance is woven into time. Still, the deeper mystery remains. Why does space-time have this structure? One possibility is that the limit is fundamental. Perhaps asking why the universe has an invariant speed is like asking why it has 3 large dimensions of space, or why logic preserves cause before effect. There may be no simpler layer beneath it. The rule may simply be part of what this universe is. But physics has often revealed that things once considered fundamental were not fundamental at all. Heat was once treated as a substance. Later, it became understood as the collective motion of particles. Atoms were once thought indivisible. Then they opened into electrons and nuclei. Nuclei opened into protons and neutrons. Those opened into quarks. It is possible that space-time may one day follow the same pattern. Perhaps space and time are not the deepest ingredients of reality. Perhaps they emerge from something more basic. Some approaches to quantum gravity suggest that geometry may arise from networks of relationships, quantum information, or patterns of entanglement. In such ideas, distance may not exist at the deepest level. Time may not flow in the familiar sense. Space-time could be a large-scale appearance produced by an underlying structure that does not resemble a smooth universe at all. If that is true, the speed of light might also emerge. It could be the maximum rate at which influence travels through that deeper network. Like a ripple moving through a material, its speed might reflect the properties of the hidden structure beneath space-time. This is an intriguing possibility, but it is not yet a confirmed explanation. No complete theory has successfully united quantum mechanics and gravity in a way that has been experimentally verified. We do not yet know whether spacetime is fundamental, emergent, discrete, continuous, or something our current language cannot properly describe. There are also theories that question whether the speed of light has always played the same role throughout cosmic history. Some speculative models explore whether conditions in the very early universe allowed different behavior. Others investigate whether Lorentz symmetry could break at incredibly high energies. So far, however, observations have strongly supported the familiar relativistic structure. Light continues to arrive as though the same boundary governs the universe across immense distances and ancient eras. The honest answer, then, is both satisfying and incomplete. We understand what the limit does far better than we understand why it exists. We know that without such a boundary, the universe we recognize might not remain coherent. If information could move arbitrarily fast, the distinction between before and after could become unstable. Causal order could depend on the observer. Signals might form loops through time. The limit prevents ordinary influence from escaping the geometry of light cones. It protects the sequence by which one event can lead to another. Perhaps this is why the boundary feels less like a restriction and more like an organizing principle. It does not merely prevent us from moving faster. It gives reality a structure. It allows the universe to have local causes, separated histories, and meaningful distances. It ensures that information requires a journey, that every connection must cross space and consume time. And perhaps this is the deepest clue light has offered us. The universe is not a single object revealing itself everywhere at once. It is a web of events, gradually exchanging influence. Each event reaches outward. Each signal travels. Each observer receives only what has had time to arrive. The speed of light may not provide the final answer to why reality exists as it does. But it tells us where the mystery begins, and after traveling to the farthest horizons, we can now return to the smallest distance of all, the quiet space between the screen and your eyes, where another particle of light is completing its journey. And now, after crossing the universe, we return to the quiet room where this journey began. The screen glows softly in the darkness. From its surface, countless photons are leaving every second. Most travel past you. Some scatter from the walls, and a few complete the small journey between the screen and your eyes. The distance is tiny. The travel time is almost impossible to notice. Yet even here, light does not arrive instantly. The image you see belongs to a moment that has already passed, only a fraction of a second ago. But still, the past. This is true of everything you have ever seen. The moon, the face of someone you love, a distant mountain beneath the evening sky, your own reflection in a mirror. Seeing is never the direct possession of the present. It is the reception of light from what has already happened. Across a room, the delay is invisible. Across a solar system, it becomes minutes or hours. Across a galaxy, it becomes thousands of years. Across the observable universe, it becomes billions. The same rule quietly connects the smallest glance with the oldest light in existence. And through that rule, the speed of light shapes far more than illumination. It shapes time. It prevents the universe from sharing one universal present. It allows two observers to measure different durations and still both be correct. It causes the traveler who crosses the stars to return younger than the world left behind. It creates the boundary between events that can influence one another and events that remain separated. It tells every cause how far its effect may travel. It defines the horizons of black holes. It limits the regions of the cosmos that can ever send us a message. And it ensures that some galaxies, though still visible through ancient light, are already beyond any future journey or conversation. Light connects the universe, but it also reveals how deeply the universe is divided. Every photon carries information from one event to another. A star burns. A wave of light begins. Years pass. Worlds move. Civilizations may rise and disappear. And eventually, somewhere far away, an observer receives a small piece of that vanished moment. The universe is filled with these delayed messages. Some are crossing rooms. Some are crossing oceans. Some are moving between planets. Some have been traveling since before Earth existed. None arrive from the present. They arrive from layers of history. Perhaps this is why the night sky feels so peaceful. Its stillness is not the stillness of things happening together. It is the stillness of distant moments finally reaching us. A star from 8 years ago. Another from 500 years ago. A galaxy from millions of years ago. An ancient afterglow from the childhood of the cosmos. All of them gathered above one quiet world. We began by asking why reality should have a speed limit. We found no final answer. Physics can describe the limit with extraordinary precision. It can show how space contracts, how clocks separate, how horizons form, and how causality remains protected. But beneath those explanations, the deepest mystery remains. Why should reality be built this way? Why should every connection require time? Why should no observer ever see the universe all at once? Perhaps a future theory will reveal a deeper structure beneath space-time. Perhaps the speed of light will emerge from something more fundamental. Or perhaps this boundary is simply one of the quiet rules from which every possible moment is made. For now, light gives us something more valuable than a complete answer. It gives us a map of the mystery. It shows us that space and time are woven together, that the present is local, that distance is also delay, that the visible universe is an archive, and that reality is not one enormous instant, but a web of events slowly sharing themselves with one another. Another photon has now crossed the room. It reaches your eye. For that brief moment, a piece of the universe arrives, already old, already gone. And perhaps the strangest thing revealed by the speed of light is not simply that the universe has a limit. It is that this limit quietly shapes every distance, every moment, and every possible connection between one part of reality and another. Light allows the universe to be seen, but its finite speed ensures that no observer will ever see it all at once.